Dear students, let us continue learning the course Automata Theory and Computability. We are in the 7th session of the module 4. The topics covered under this session are variants of Turing machines. Myself, Dr. Suresha.d from the Department of Computer Science and Engineering of Canara Engineering College, Bantwad, Mangaluru. Before we start off with the variants of Turing machines, let us brush up the things what we learnt in the previous video. So in the previous video, we learnt on the techniques for Turing machine constructions, under which we learnt Turing machine with stationary head, multi-track Turing machine, storage in the tape and the subroutines. So now let us continue further and let us learn the variants of Turing machine in this lecture. So to start with, there are mainly two variants are there in the Turing machines. So if you take up a standard Turing machine, so there we learnt two concepts over there. The first one is a single tape, single track Turing machine. Single tape and the single track Turing machine. And the second one is single tape but multi-track Turing machine. It was a single tape, but that tape was divided into the multiple tracks. Single tape and the multi-track Turing machine. So these are the two techniques in the design of the Turing machine. That is a single tape, single track Turing machine, and a single tape, but that tape is divided into multiple tracks. So these things we learned in the previous video. Now let us continue further, and now we will learn the variants of the Turing machine. The two main variants of the Turing machine are, the first one is multi-tape Turing machine. First one is a multi-tape Turing machine, and the second one is non-deterministic Turing machine. So for the multi-tape Turing machine, so here in case of the previous cases we used to have a single tape. Now we will have the multiple tapes. So multiple tapes will be there. So that is, we may have more than one tape. The Turing machine with more than one tape, we call it as the multi-tape Turing machine. Right? So there for each tape, one different head will be there. That we will see in detail. And the second variation is non-deterministic Turing machine. So non-deterministic Turing machine you can compare with your non-deterministic finite state machine. So in the non-deterministic finite state machine, what happens? There will be more than one movement is possible for the same input symbol. So if we remember our previous design of the previous finite state machine, so now, so this will be in a deterministic model wherein for each alphabet single transition will be there. So if I have more than one transition or on the same symbol, now if you observe over here on Q0 I have the two transitions on it. One to the Q0, other to the Q1. Right? So this was the case what we learned in the deterministic and the non-deterministic finite state model in the module 1. So now the same thing is extended for the Turing machine. So in the case of Turing machine, what happens? How we will write the transitions? So it can be written as Q0 on A. So I may go to the state Q0 only. A I will replace as it is, and I can have the left movement. And one more I can write it as I can go to the state Q1. I can have the A as it is, and I can have the right movement. For the same state, same input symbol, I have more than one transition is defined. For the same state, same input symbol, I have more than, not input symbol here, same tape symbol. For the same state, same tape symbol, I have more than one transition defined For each tape, I may have the different direction of movement. The movement can be a left movement, or it can be a right movement, or it can be a stationary, because we learnt in the previous session. Even we can have the stationary head may also present over there. Stationary head may also present over there. Fine. So all these things comes under your non-deterministic Turing machines. So in the non-deterministic Turing machine, what happens? Now we have the transitions delta of Q on A. It may be the first pair, that is from Q to, I will go to the Q1 to P1, A is replaced with Y1, direction may be D1. Or I may go to the state QP2 and A I may replace with Y2, and I can have the in the second direction. In the same way, I can have the or such combinations may be present over there. Such a scenario we call it as a non-deterministic Turing machine. Rest of the things remains same. Rest of the things remains the same. That is the states and all the things remain same. Only the variation in the delta function. What that variation? We may have more than one transition may be there for the same state, for the same tape symbol. Such an transitions we call it as the non-deterministic Turing machine. Such transitions we call it as a non-deterministic Turing machine. Fine. So now let us go for the first variant of the Turing machine, multi-tape Turing machine. In case of the multi-tape Turing machine, we have a finite state Q, which indicates the number of states over there. The initial start state, let me call it as a Q0, and F be the subset of Q, which will be your set of final states or the accepting states, what we use in our terminology. And we can have the P tape symbols. We may have the P tape symbols, that is nothing but your tau. The next will be your blank. So blank is not part of sigma, you need to remember. Blank is not part of sigma. Sigma is your set of input symbol. Sigma is a subset of a tau symbol. What is tau? Tau is a set of tape symbols. Tau is the set of a tape symbol. So sigma may be subset of tau. So sigma is a subset of tau. But blank is not a subset of a sigma. Blank not belongs to sigma. Blank is a blank symbol what we use. Then next, if you go with the architecture of the multi-tape Turing machine. So now if you observe this architecture clearly, so now we have a finite control and we have the n, in this case we have the 3 tapes over here. I have the 3 tapes. For each tape I have a different head. For each tape I have a different head which is present. And that is for each tape the movement may be different. The first one may be left movement, for the second one it may be right movement, for the third one it can be stationary movement. So for the first one if we take up, how we can write let the state be Q0, Q0, let A x1 or A be the alphabet on the tape symbol of the first tape, then I can write it as a Q0 to Q1, A I can replace with X, and I can have the left movement. Then next for the second tape, Q0, second tape let it be B, then it can be written as a Q0, I will go back Q1, then I will replace with X, I will replace with Y, and I can have the right movement. In the same way I can go for the third tape, Q0 on C, I can go to the state Q1, Q2, any state I can use over here, no problem. Then next I can replace with the Z and I can be stationary. When such an arrangement wherein for each tape the movement may be different. The movement may be left, the movement may be right, or the movement may be stationary. The same thing if you compare with your multi-track Turing machine. So in case of multi-track Turing machine, what happens? Finite control will be there, but there will be a single head. So there will be a single head, but the tape is divided into multiple tracks. 1, 2, 2, 3 and the 4. It will be divided into the multiple tracks. So now it will be written like this. So how we write there? Q0, and on all the tape symbols, the track symbols can be all together. Let me put A, B, C, D. Where A is on the first track, B is on the second track, and C is on the third track, and D is on the fourth track. Fine. Those are the track symbols. Now that can be, you can write it as a Q1, A I will replace with X, B, Y, C, Z, and D I will replace with P. but I will have the left moment. So now only one moment is allowed. Only one moment is allowed, left or the right. I can't, for the track wise, I can't have the separate moment. But for the multi-tape Turing machine, for each tape I can have a different moment. For each tape the moment may be different, but for the multi-track Turing machine it is not so. We have to have a common moment should be present. Fine. That is the main variation between your multi-tape and the multi-track Turing machine. Their single tape, K tracks. Here we will have the K tape only, and each tape will have the single cell there, it will be there. And for each tape one head will be there, and that head the head moment is independent. The head moment of the first tape may be different from the head moment of the second one, it can be different from the head moment of the third one. But generally the first tape, the Q0 will start from the transitions from the first tape. First tape it will start, from there it will continue. Fine. So now if we go in detail, there will be K tapes will be there, and each tape is divided into number of cells. The first tape holds your input string W initially, all the other tapes will hold the blank symbols. Initially the head of the first tape, input tape, is at the left end of the W, and all the other heads can be placed at any cell initially. Delta is a partial function we are telling, fine, that is multiple transitions may be there. That is a Q on tau power of K, where K is the number of tapes and tau is the tape symbol. So now for each tape we can have the different moment, the left, right and the stationary, which is allowed for your multi-tape Turing machine. Fine. So now a move depends on the current state and the K tape symbols under K tape years. A typical move may be M may enter into a new state. On each tape a new symbol is written in the cell under the head. Each tape head moves to the left or the right or remains stationary. The head movement is independent. Some can move to the left, some to the right, and some may remain stationary over there. The initial instantaneous description as the initial state Q0. The input string W is kept on the first tape, that is input tape. Empty strings are the blanks in the remaining K-1 tape. The accepting instantaneous description has a final state. Some strings in each of the K tapes may be there. Now let us learn some of the theorems on the multi-tape Turing machine. The first theorem: every language accepted by a multi-tape Turing machine is accepted by some single tape Turing machine. That is the standard Turing machine. Okay. So now the theorem proof is quite simple. So now we need to prove that a language which is accepted by a multi-tape Turing machine is accepted by a single tape Turing machine. That is the standard Turing machine. So now the proof starts with, suppose a language L is accepted by a K tape Turing machine. Let that machine be M. This can be simulated with a single tape Turing machine with 2 K tracks. So now the K tapes, these are the tapes over there. So now 1, 2 go on up to K. So we have the K tapes are present. So now those K tapes will be simulated with the help of the 2K, 1, 2 till go on up to 2K. 2K number of 2K track. 2K track means it is a single tape but multi-track Turing machine. Now the second, all the even tracks, that is the second, 4th, 6th, the last one is 2K. That is the second, 4th and the 2K track will hold the content of the K tape. And what about the odd one? The odd will hold the head marker. The odd will hold the head marker over there because the head is common over here, not as the multi-tape. In the multi-tape, head is different. But in case of multi-track, we have the common head will be there. So the head marker will be kept in the odd position to indicate the position of the respective tape head. Then we give an instantaneous, that is your implementation description of the simulation of M with a single tape Turing machine. We give it for the case of K equal to 2, that is the double. The construction can be extended to the general case. So now in the figure in the next slide, which will visualize the simulation, you can observe carefully. So now it is the multi-track, not the tape. So that multi-tape, we are creating a equivalent multi-track over here. So now all these are our input symbols, A and the B, they are our input symbols. Now for the K, they have taken a size of 2. So that is a 2 tapes. So now for the simulation, we are using the 2 into K, which is nothing but 4. 4 tracks are present. For the simulation of a 2-tape Turing machine, we are using a 4-track standard Turing machine. So now on the even number of tracks, that is the track number 2 and the track number 4 will have my data. The track 2 will have the data on the A, the track 4 is having the data on the B. Then the track 1 and the track 3 will have the header information. The header information is a X, which will be kept over here. Fine. So that is initially the contents of the tape 1 and 2 of the machine M are stored in the second and the fourth track. That is the tape 1 contents are stored in the second track. Tape 2 contents are stored in the fourth track. The head markers of the first and the third tracks are at the cells containing the first symbol. To simulate a move of the machine M, the 2K track Turing machine M1 has to visit 2 head markers now. So now it is not the single head marker. Now we have the 2 head markers here. So now the 2 head markers and store the scanned symbols in its controls. Keeping track of the head markers visited and those to be visited is achieved by keeping a count and storing it in the finite control of M1 dash. So here the finite control of M1 has also the information about the states and its move. That is your header information. Right? After visiting both the head markers. So M1 knows the tape symbols being scanned to the 2 heads of the M. The next. For each M1 revisit each of the head markers, it will change the tape symbol in the corresponding track of the M1 based on the information regarding the movement of the machine corresponding to the state. So depending on the state, we make the changes in the track and the tape symbol in the corresponding tape pen. Then we move the head markers to the left or the right. M1 changes the state of the M in its control. So this is the simulation which will be done with the simulation of a single movement of the machine M. Right? So now how we have simulated, to summarize this one. Suppose we have the K tracks which are present, K tapes which are present in a multi-tape Turing machine. If I want to construct an equivalent single tape Turing machine, we will construct in a single tape multi-track Turing machine with the number of tracks will be equal to 2 into K. And for each tape content are copied to the even tracks of the multi-track Turing machine. And the odd track 1, 3 and the 5 will have the header movement. And depending on the header movement and the symbol under scanning, we will go for changing the state. How we will do for the tape? Now for the tape, each tape we have the 2 things are there. One will be the header and other is our data. So now these 2 things we will alter for that tape content. So now the thing which can be simulated with the multi-tape Turing machine can be simulated with the help of the multi-track single tape standard Turing machine. Right? Now the second theorem. If M1 is a single tape Turing machine simulating multi-tape Turing machine, then the time taken for simulation is big of n square. Big of n square. So now let us observe the movement of the head in case of the K-tape Turing machine over here. So now let M be a K-tape Turing machine. After n moves of the M, the head markers of M1 will be separated by 2 n cells. So now if we go with the movement over here, the head markers, the one can be move 1, so 1, 2, 3 and the 4. Let me take an example of K equal to 2. So now if in case of this one, what happens now, if I have the head over here, the first head of, so these are the 2 tapes, tape number 1 and the tape number 2. If the first one is move, we have the n movements. If the first one will move in the n left direction and the second one will move in the right direction. So now what is the distance it is moving? N. What is the distance it is moving? N. So now what is the distance between these two? N plus n. What is the value over there? 2 into n. Maximum. Right? That is after n moves of the movement, the head markers of m1 will be separated by the 2n cells or the less. Obviously, it will be either 2n cell or the less will be there. Right? Then at the worst, one tape movement can be to the left by n cells and the other can be to the right by the n cells. So in this case, the tape head markers are separated by 2n cells. Now in the rest of the cases, the gap between may be less when compared to the 2n. The maximum value is 2n. To simulate a move of the machine M, the tape M1 must visit all the k headers. So it should visit all the k headers over there. So now how many k headers are there? Total k such headers will be there. K headers. If M starts with the leftmost head marker, M1 will go through all the head markers by moving to the right at most 2n cells. So we can have that the distance apart, it will that 2n is the distance apart. So now we need to have the k head markers to be visited over there. So now what happens? It will be equal to 2n plus 2k. It will be equal to 2n plus 2k movements will be done. That is 2n plus 2k movements to the left for simulating the change in the k tape. Now the number of movements for the n will be equal to, if you add up that one, this will be, for one side it is 2n plus k and other one is 2n plus k. So when we add up this one, how much we will get? 4n plus 2k. 4n plus 2k. So like this we need it for the n such movements. So that will be equal to 4 into n square plus 2 into n into k. So what is the highest degree over here? N square. So the complexity of the time taken will be big of n square. So the complexity will be big of n square over there. That is the proof for this one. That the complexity for that movement will be big of n square. The next one, non-deterministic Turing machine. So in the non-deterministic Turing machine, so if we compare the non-deterministic Turing machine with the deterministic Turing machine, how the deterministic Turing machines will be? First, Q naught on A. Let me write as a diagram here. Q naught on A. I will go to Q1. A I will replace with X and the right moment. So this is the deterministic Turing machine. If we go for the non-deterministic one, how it will be? Q naught A X and the right, I will go to Q1 and I can have more than one transition. A I will replace with Y and the left moment. So now if we go for writing the moment over here, how the moment will be? Q naught on A, we go to Q1, A is replaced with X and the moment is right. So in this case I have the two moments over here. What are the two moments? Q naught on A, the first moment will be Q naught itself, A I replaced with Y and the left moment. Second one is Q1, A I replaced with X and the right moment. Fine. So that is the rest, it is remains the same thing. The only changes is there with your transitions. So in case of non-deterministic Turing machine, we may have more than one transition may be present. We may have more than or zero transition may be present. Fine. So we may have more than one transition may be present. Such a scenario we call it as the non-deterministic Turing machine. If we go with the formal definition of the non-deterministic Turing machine, it will have the 7 tuple. What are 7 tuple? The first one is Q. What Q is? Q is the set of states. Sigma. What is sigma? Set of input symbols. Tau. Set of tape symbols. Delta. This is important. Delta is a transition function. Delta, the transition function is a partial function. What is partial? We may have n transitions may be defined for a same state, same input symbol. For the same state, same input symbol, we may have n transitions may be defined. That's why it is called as the partial function over there. That's why it is a partial function. Then next one, Q naught, start state, B, blank space. F subset of Q. What is F? F is a subset of Q. So what F indicates? F indicates set of accepting states are the final states. Set of accepting states are the final states. So these are the 7 tuple of the non-deterministic Turing machine. The most important is this one, the delta. The delta is a partial function from Q to tau, is a power set. We can have the 2 power n combination. That's why it's a power set. It's a power set of a Q cross tau. It is the left or the right movement may be there. Next, the first step. If M is a non-deterministic Turing machine, then there is an equivalent deterministic Turing machine is also there, and both are equal. Fine. So if you remember our first module, so there we have done the equivalence of non-deterministic finite state machine with the deterministic finite state machine. So and we proved that these two are equivalent. That is, every non-deterministic finite state machine can be converted into a deterministic finite state machine. How we have done? We started with the epsilon closure of the start state, then we continued. What are all the possible reachable states were there? We grouped and we made. We have grouped and we have constructed into the deterministic finite state machine. Same thing, but with a different logic, we are going to prove this theorem. Fine. What is our theorem? If M is a non-deterministic Turing machine, then there is a deterministic Turing machine M1. So M1 is the equivalent of M that we need to prove. That the Turing machine M is equivalent to Turing machine M1 that we have to prove now. Fine. The proof will be done with the help of the construction. Fine. So now we construct M1 as a multi-tape Turing machine, because in case of non-deterministic Turing machine, we may have more than one transition may be present, and that more than one transitions let us simulate by the help of the multi-tape Turing machine. For the first case, we write the contents to the first tape. Second case, second tape. Third case, third tape. Like that is, we construct M1 as a multi-tape Turing machine. Each symbol in the input string will lead to a change in the instantaneous description. M1 should be able to reach all possible instantaneous descriptions and stop when a description containing a final state is reached. So the first tape is used to store the instantaneous description of the tape of the machine M as a sequence and also the state of the machine M. These descriptions are separated by the symbol star, which are included as a tape symbol. The current instantaneous description is known by making an X along with the instantaneous description star. The symbol star is marked with a X with a new tape symbol. And all the instantaneous descriptions to the left of the current one have been explored already and so can be ignored subsequently. So here the current instantaneous description is decided by the current input symbol of W. How the illustration will be done? Fine. So here the machine 1 examines the state and the scanned symbol of the current instantaneous description. Using the knowledge of the moves of the machine M stored in the machine control M1, it checks whether the state in the current ID is an accepting state or not. In this case, if it is an accepting state, you accept it, or if you accept, then you stop the simulation. If the state Q, say it is of the format like this, X, Q, A, Y, what is there under the tape? A, fine, is not an accepting state of M. Then delta Q upon A as a K triples. If M1 copies the ID X, Q, A, Y in the second tape and make K copies of the instantaneous description at the end of the sequence of the IDs in the tape 2. Then M modifies these K IDs of the tape 2 according to the K different choices which are defined using the transitions. Then M1 returns the marked current ID, erases the mark X and marks the next ID separator with the stop with the X. Then M will goes back to the step 1, which is depicted in this figure. So now these are the instantaneous, all the possible instantaneous description, they are separated with the star. We start with the initial instantaneous description and we copy it to the tape 2. That is, M1 stops when the machine is in the accepting state. M is reached with the step 1. Then M1 accept the input string W only when it is able to find what that M has entered accepting state after the finite number of moves. This is clear from the simulated sequence of the moves of the machine M1. Then we can prove that M1 will eventually reach an accepting ID, that is an ID having an accepting state of M if M enters an accepting ID after N moves. So here each move of M is simulated by the several moves of M1. For the each non-deterministic move, we will make several moves in the deterministic model M1. Let M be the maximum number of choice that M has for various Q upon A. It is possible to find M since we have only finite number of pairs of Q upon tau. So for each initial ID of M, there are at most M instantaneous descriptions that M can reach after one move, at most M square IDs, that each M can reach after the 2 moves. So if we continue that one, the sequence we will get as 1 plus M square up to M power of N. So hence the number of IDs can be explored under M1 is N into M power of N. Then we assume that M1 explores all these instantaneous descriptions, and these descriptions have a tree structure having an initial ID as its root. Then we can apply the breadth first search for the nodes of the tree. What is our depth first search? We visit all the nodes at that level. We visit all the nodes at that level. If M reaches an accepting ID after N moves, then M1 has to search at most M power N IDs before reaching an accepting ID. So if M accepts W, then M1 also accepts W, hence these two are equivalent. Fine. So these are the contents under the variants of the Turing machine. The things what we learned under the variants of Turing machines are, the first one is a multi-tape Turing machine and the second one is a non-deterministic Turing machine. And in the multi-tape Turing machine, we proved that they are equivalent to standard Turing machine, and non-deterministic Turing machines are also equivalent to standard Turing machines. The references for this presentation are taken from the textbook KLP Mishra, N. Chandrasekharan, 3rd edition, Theory of Computer Science, PHI 2005. Thank you.